Now let's talk about properties of a Z-transform. First, Z linearity. As we have Xn, whose Z-transform is Xz, and the region of convergence is ROCX. And we have Yn, whose Z-transform is YZ, and we have ROCY. Now suppose we linearly combine X and Y together to get W. What would be the Z-transform of W? Would it be the linear combination of X and Y? By definition, WZ is Wn Z minus n, and we should put Wn here. Wn should be put in here, and then Z minus n, summation over all n. We can split it into two summation because we want to make it related to the Z-transform of X and the Z-transform of Y. So let's split it into the term of X and the term of Y. Then we see that this is indeed the Z-transform of X, and this is the Z-transform of Y. So in the end, indeed, it would be a linear combination of the Z-transform of X and the Y. How about regional convergence? WZ converges to the linear combination of the linear combination AX plus BY. If this term converges to this term and this term converges to this term, that means whenever Z is in the regional convergence of X and the regional convergence of Y, then WZ will converge to this expression. This means the regional convergence for W and the regional convergence for X and the regional convergence for Y. Whenever Z is in the intersection of ROCX and ROCY, it will always be in ROCW. So ROCW should contain this intersection. We said ROCW contains the intersection instead of equal to the intersection. Does it ever happen that ROCW is not the same as the intersection? Does it ever happen? Let's consider the example that y is equal to minus x, and x is the example one-sided exponential sequence. Then we see that suppose w is equal to x plus y, it will be 0 in this case. And the ROC of w will be the whole C-plan, the whole complex plan, whereas ROC x and ROCY, they are the same thing. If we consider the exponential sequence pk raised to the power n un, we know the Z-transform would be 1 minus pk Z inverse for all Z that's greater than pk, absolute value. So if we want to get the Z-transform of x, we can simply linearly combine these Z-transform. And the regional convergence will simply be the intersection of them, of all these regional convergences. So we will make, so Z should be greater than the maximum of all these poles. We can find out the poles of XZ. P1, suppose this is P1, this is P2, and this is P3, and we compare their absolute value and say, and find out the largest, the one with the largest absolute value, and the regional convergence will be all the collection of Z that's outside the largest P absolute value. One very important property, convolution property. Suppose y is the convolution of x and h, then the Z-transform of y is equal to x and hz, the product. And the region of convergence is a set that contains the intersection of ROC x and the h and ROCY contain this intersection. The proof is quite straightforward. We plug in the definition, we use the definition of the Z-transform. YZ is equal to YN Z minus N. So in this bracket here, we should insert YN, which is the convolution of X and H. So put down XK and HN minus K here. Summation over all K. This will be YN. When we have two summation, usually a good idea to switch the order of the two summation. So let's do that. K, and we have xk, and the inside we have another summation, h and minus k here, and the z, this is z minus n, but we want to make it more like a Z-transform. So let's put down n minus k here, and we will need to compensate the extra term, so let's put down z minus k. This term here look a little bit like a Z-transform, but it's a little bit different, so let's take a look at what it is. This green term here would depend on k, so let's try it out a few possible choices of k and see what it is. For example, when k is equal to 0, then this term becomes hn z minus n summation for all n. And what is this? This is hz. In the case that when k is equal to 1, we get summation over n, hn minus 1, z minus n minus 1. Let's make a change of variable here. M is equal to n minus 1. Then we can sum over m and hm. And we have hm and the z minus mk. And we sum over n from minus infinity to infinity. M would also be from minus infinity to infinity. And then we see that this gives us hz again. More generally, when k is equal to k0, then this is a, then we have hm minus k0, z minus m minus k0, sum over n, and we can play the trick of change of variable again. M is equal to n minus k0. Again, we get hz. So this one here is really independent of k, and it's always equal to hz. It's independent of k. Because it's independent of k, we can pull it out, the summation, and we see that the first term here is actually xz. So we have yz equal to the product of h and x. For example, hn is the impulse that's delayed by 1. Then hz, if we plug in hn, then we get, there's only one non-zero term. The non-zero term is the one when n is equal to 1. So we get z minus 1. Now suppose yn is the convolution of x and h. Then in the z domain, we know it's simply the product of xz and hz, which is equal to the inverse. And that's why when we talked about the delay system earlier, the output is a delayed version of the input by 1. Then we put z inverse here because that's the Z-transform of the impulse response of the delay system. Like the case of continuous time system, whenever it comes to system, what's put in here, remember we always put the impulse response of the system of an LTI system right in the bracket, right in the box. And it happened more often that instead of putting impulse response in the box, we put the Z-transform. That is more common. Another example, suppose Hn is the one-sided exponential sequence and Xn is delta n minus half delta n minus 1, and what we can see is that Hn is a right-sided sequence that we have seen earlier. This is Hn, and whereas Xn has only two samples, one at 0, one at n equal to 1. It's like this. This is the sequence Xn. Now we want to find y. That is the convolution of x and h. We can, of course, do it in the time domain like we did before. And now we have the option of using Z-transform to find out the output. Remember, YZ is the product of XZ and HZ, right? So let's find out what HZ is. We are very familiar with this exponential sequence now, and this is its Z-transform. And XZ, let's also find out its Z-transform. Y is the product of the two. So we have H and then X. And one thing that happened is these two cross out and becomes 1. A Z-transform that's equal to 1, what is Yn in this case? It would be delta n. And the regional convergence is the whole Z-plane. And of course, it contains the intersection of the regional convergence of X and the region of convergence of H. The regional convergence for X in this case will be whole Z, the whole Z-plane, except Z equal to 0. Now let's talk about inverse Z-transform. From Z-transform and the regional convergence, we can determine the corresponding time domain sequence. Two most popular approaches for finding the inverse Z-transform, for doing the inverse Z-transform, is inspection and the partial fraction expansion. Both of these two methods are for rational XZ. For non-rational XZ, long division or power series or Cauchy integral can be used. Of course, for rational XZ, we can also use a long division or power series or Cauchy integral, but inspection method and the partial fraction expansion are the most convenient. For example, this is our HZ, has ROC, that is the whole Z-plane except for the origin. Then we can see that this is one of the examples that we have worked with before. Hn is equal to a quarter for n between 0 and 3, and it's a 0 otherwise. More generally, if we have a Z-transform of this form, that is a summation n from 0 to n, alpha nz minus n, and the region of convergence is the whole Z-plane except for the origin, then we also know what the corresponding sequence is. Hn is equal to alpha n for n between 0 and m, and it's a 0 otherwise. Another example, if this is xz and it converges for all z greater than half, and this is also one example that we have worked with before. We know what the corresponding time domain sequence is. It's the exponential sequence, one-sided exponential sequence. Now this xz, the regional convergence is inside a circle, so it's a left-sided sequence, and we have seen such an example before. It's 2 to the n, u minus n. For these three simple examples, we have used an inspection method. Now let's use partial fraction expansion for a more general rational Z-transform. For a more general Z-transform like this one, it has denominator in polynomial in Z inverse and a numerator also a polynomial in Z inverse, and there's no multiple poles, and the order m here is smaller than n here, then we can use partial fraction expansion. If regional convergence is outside a circle, then we know this is a right-sided sequence. And we have seen, and we can use partial fraction expansion to rewrite it. We can rewrite xz as a sum of a first order term like this. And we have seen such a Z-transform before. When x is a sum of exponential sequences, then each exponential sequence will give us a first order term. So xz will be a sum of first order terms. So we have xn is a sum of exponential sequences. In the case that m is larger than n, then we can pull out terms from the numerator, and we now have c0, c1, z inverse up to cn minus n, and z minus n minus n. And the rest of the term in the numerator is the leftover terms, and the denominator stays the same. And now we can apply Z-transform on this part and this part separately. For the second part, we can apply partial fraction expansion like we did earlier. And for the first part, we know that if we apply the inverse Z-transform, it would give us C0 delta n plus C1 delta n minus 1 all the way to C n minus n and delta n minus n minus n. In the discussion of discrete time Fourier transform, we saw that when a sequence is real, the Fourier transform has some special properties. Now let's see if we have such properties for Z-transform. When a sequence is real, let's take conjugate on both sides, then everything will be conjugated, and xn conjugated is the same as xn, so it stays the same. And this is the same as xn, z conjugate minus n. And we see that this is the Z-transform of x, except that z is replaced by z conjugate. So the conclusion that we get from here is that the Z-transform of x at z conjugate is xz conjugate. What does this mean? So if this is z0 here, this is z0, then where is z conjugate? Z0 conjugate will be here. And the value of x at these 2 points are compass conjugate of each other. In particular, if z0 is a 0 of x, so x z0 is equal to 0, then we know x z0 conjugate, whose value is the conjugate of x z0, would also be 0. This means the zeros of x are in compass conjugate pair, except for zeros on the real axis. Similarly, the poles of xz are in compass conjugate pair, except for poles on the real axis. Earlier we have talked about stability of LTI systems. Given an impulse response Hn, we know the system is stable if and only if the impulse response is absolutely summable. And it turns out that the condition can be also given in terms of Z-transform. This is the Z-transform of Hz. And if we look at the unit circle, Z is equal to Ej omega, then we have Hej omega equal to Hn E minus J omega n. And if you take the absolute value on both sides, this is what we get. And we know the absolute value of a sum is less or equal to sum of absolute value. And the multiplication of an each E minus J omega n has unit magnitude, so this is what we get. And that is the sum of absolute value of Hn. If the ROC contains unit circle, we know this converges. If ROC contains the circle Z equal to Ej omega, then this converges, this is sum converges, and the system is stable. The circle Z equal to Ej omega, this is the circle Z equal to Ej omega, is given the name unit circle because it has a unit radius. A question: suppose H is causal and stable, what would the regional convergence look like? If it's causal, then its regional convergence should be outside a circle. But it's stable, so this region should also contain the unit circle. So there's only one way to go. It should be a circle. The regional convergence should lie outside of a circle, and this circle is inside the unit circle. Now let's consider a very common case where Hz is a rational transfer function and it has poles at P1 to P2 and Pn, and it's causal and it's stable. If it's causal and stable, from the previous result we know that the region of convergence is outside a circle and the circles lie inside the unit circle. On the other hand, when H is causal and poles at P1 to Pn, we know its regional convergence is outside of a circle and the radius is the maximum of the absolute value of the poles. So if we combine these two results, we know where these poles should be, right? They cannot go outside the unit circle. The poles of a causal stable filter are inside the unit circle.